we go. Okay, so in this section, we're going to talk about dot products, more about vectors. So we've now been talking about these quantities, right? Vectors are, a vector is something that has a magnitude and a direction, as opposed to a scalar, which is just a quantity, right? It's just a plain old number. So now, a dot product is actually just a scalar. It's just a simple old number, right? So let's talk about what a dot product is. So we've been talking about components of vectors, right? So suppose here you have vector A and vector B, right? The green is vector B. Now, we know exactly what if I say length of vector B, we know exactly what that represents, right? That's this, and it's just a scalar number, right? Like, it's 12. That's the length of vector B. Now, this is vector A. Suppose we wanted to draw the components of vector A such that one of the components lies on B, okay? So if I wanted to draw the components, take a look. This is, okay, this red and this red, are those two red lines components of vector A?
No.
Yes,
Yeah.
right?
No.
This one and this one. They are components because they add to create vector A. So these are, they're not necessarily the rectangular components, but these are a pair of components of vector A. The reason why this is special now is because one of the components lies along the other vector B. You guys getting me? Okay, so for instance, I could have also drawn components like this, but that's not what I want today because none of those lie on vector B. Instead, what I want is this component and that component. Now, remember we talked about the length of vector B, the green vector? Okay. Now let's talk about this length. Okay? This is called, that length, this red line. Okay, so I'm going to erase that one. That line is called the projection of vector A along B. Say that to impress your friends, right? This is the projection of vector A along B. All it is one of the components of vector A that lies on B, okay? So in formal terms, it's called the projection of A onto B. Now, if I found the length of that green part, if I found the length of that red part, projection of A onto B, and if I found the length of B, now I have two numbers, right? If I were to multiply those two lengths by each other, now I have another number. That is the dot product. Okay? You guys with me? So that's what a dot product is. So to find a dot product of two vectors, you take the length of one vector, multiply it by the length of the projection of that other vector onto this. And then you just get a number, 12, 15, 72, whatever, okay? Okay.
The way to write it is just projection, like the...
Yeah, it's P-R-O-J.
P-R-O-J
A and then
B.
subscript B. Yeah.
Oh, subscript.
This is a subscript. It's like a log base.
Where is the subscript?
It's like log base B or something, right?
Okay.
Yeah. I hate
So
doing
hard to
that.
see.
I really hate doing that. Okay, this is literally the only time I'm doing it. Okay, because I
It was the other one.
okay, I hate it in the dark. Okay.
No, both of them.
Okay. Was this the one?
Yeah.
Okay, so just today, yeah? Okay, yeah.
Did you put that half arrow in B too?
Yes, I did. Yes.
Could you show like how
Don't worry too much about it. Okay. So, how do you find the dot product? To find the dot product, it's actually rather simple. If you have vector A in component form, and if you have vector B in component form, what you do is you multiply these two, and then you multiply these two, and you just add the numbers to each other. So it's very, very simple. So let's take a look at this one. So, so here you have U and V. So U dot V is gonna be negative 3 times 3 plus, always plus, 4 times 6. So that is just negative 9 plus 24. So we say U dot V is 15. Okay, it's just a scalar. Okay, we'll talk about later about what that means. Now, orthogonal vectors. Orthogonal vectors are vectors where the angle between them is 90 degrees, right? So if you go to the orthodontist, what does the orthodontist do to your teeth? Straighten them, right? And if you go to an orthopedist, they will like straighten your bones or whatever. So ortho, that means like straight. So orthogonal means, you know, there is like a, you know, a straight line. It's like a 90-degree angle, all right? The word, so it's like perpendicular. We use perpendicular usually for like lines and stuff. When it comes to vectors and then vectors and a plane, the term is, that's more widely used as orthogonal. Okay. Now, so suppose you have two orthogonal vectors like this, right? So to find the dot product, okay, we take the, you know, the length of V, fine. Now we want to multiply that by however much the projection of the green vector is on the red. So how much projection of the green is onto the red? 0, right? There is no projection of this on here. So it'll be times 0, which means the dot product will be 0, which means the vectors A and B are orthogonal if and only if A dot B is 0. So when you have if and only if, this goes both ways, right? The statement and the converse are true. Meaning, if two vectors are orthogonal, dot product is 0. If dot product is 0, it means the two vectors are orthogonal. Okay? Okay. Because it's the magnitude of the red times the magnitude of the component of the green onto the red. Okay, so find the dot product of U and V. Here, dot product U dot V. And that dot, it's like the multiplication dot, right? Don't ever like omit that dot. So you don't just do UV, okay? So this will be 2 times negative 14 plus 7 times 4. Wouldn't you know it? That's 0. So A and B, so U and B are orthogonal. Okay? Okay. Okay. So the dot product follows like some of these, what do you call it? The same properties as like do numbers. I want to talk about this last one, U dot U. Okay, what does it mean to be like? What does that mean? U dot U. So suppose let's take a look at, you know, the same thing but in terms of A. So suppose this is vector A. Okay, let me make it more straight. Okay, this is vector A. Now I want to draw a second vector A. Okay, this is a second vector A. To find the dot product of A dot A, I have to take the magnitude of this, right? That's this one, times the component of the top one over this. So how much is that component? All of it, right? Because all of it lies along this. So times the component of the second one. So in short, it'll be like A dot A is the magnitude squared, okay? So that's another way to find the magnitude of something. So let's take a look here, okay? This is A. Another way to find the magnitude of this, right, is, so how were we finding magnitude before? Right, you would do -6 squared plus 5 squared, and that would be root 61, right? But now, method 2, to find A dot A, to find the magnitude, you can also just do A dot A. So that would be this dot this. Okay, so how much would that be? Oh, sorry. It's the square root of all of these, isn't it?
Which would be root 60.
So it would be the square root of 36 plus 25, root 61. Okay? Right. So to sum up, this is how we were finding magnitude of A. Just to show you that you can also use dot products to find magnitude of A, it's just the square root of the dot product in itself. So now, if you're walking along the street and somebody like passes you a vector and says, hey, find the magnitude of this, you could still, you could always do it this way, but I'm just highlighting that the dot product is also another way to get there. Yeah.
Okay, but then the next step after the A.
It is more complicated, yeah.
A plus A, right? Because then you're adding the 36 to the point.
Right, so if you do A dot A, so if you do the dot product of these two, you're going to do this times this plus this times that.
Gotcha.
So it ends up being exactly what we did from the beginning. Okay? All right. So now we can use this to find the angle between the two vectors. Okay? So if you have a setup like this and you want to find this angle theta, well, the formula is cosine of theta is, what is cosine of theta here? So suppose this is x, right? How would we find x if this is just a right triangle? How would we find it?
Cosine of theta equals.
So if this is,
Yeah, X over A.
Cosine of theta equals X over A.
Okay, so if this is a, right, so cosine of theta is equal to x over a. So how much is that x? A cosine theta. Yes? So now, okay, so now how would we find A dot B? A dot B is, Max, can you put away your calculator and just be with us for a little bit? Okay, so A dot B is how much? It's the length of B, right? Times this projection, which is the x, remember? So how much is that? A dot B is B. What did we say the projection was? A cosine theta, right? Okay, so look, how do we find the dot product? It's this length times this length. We just said this length was A cosine theta, yes? Okay, so A dot B is that times A cosine theta. But this is like the magnitude of A, right? So how can we solve this for cosine theta? It's A dot B over, I divide by this, right? So B and A. That's cosine theta. Is everybody with me on where we got this from? Okay? So if this was like at level pre-calc, I would just say, here's the formula for cosine theta, memorize it. But here, I really want you guys to know where things come from, right? So this is where all that comes from. We just did A dot B, it's this times that, and then we solved for the cosine of theta. So, long story short, if you want to find the angle between the two vectors, this is the formula that you're going to use, okay? All right, so let's take one. Sorry guys, I need to turn on the lights. I can't. I'll try to write a little bit bigger.
Why is it magnitude? No.
It's magnitude here because so what is this? How much is this? Right? So cosine of theta is that magnitude over the magnitude of A, right? So these are both magnitudes. Okay? Yeah.
Do you always have to put in the absolute bracket sign? Like you just write A?
If it's magnitude, we generally need to put the magnitude sign. Okay? Because if not, if this was just like vector A, then I would put in like the component form in the brackets, right? Like 8, 3. But if it's magnitude of A, then I do like the square root of 61 or something. Okay? Yeah.
So then on top, when you have A times B, is that also, will that end up in a component form or no?
Okay, so no, because A dot B is not. Okay, so let's do an example. So find the angle theta between the two vectors U and V. So the formula is cosine theta is U dot V over U times magnitude of V, like this. Okay? I'm gonna travel a little bit today. Just get a different perspective. All right. So, yeah, like a social experiment. Okay. So now we need to do the different parts of this. Okay. So first, U dot V. Okay. Let's find U dot V. It's going to be 1 times 2 plus -4 times 6. So this will be -22. Now, I need to find the magnitude of U, which is going to be 1 plus 16, so root 17, right? From here, magnitude of U. Then I need to find the magnitude of V, which is going to be 4 plus 36, root 40. Now, this is not a final answer, so don't simplify, right? If this was a final answer, you would have to simplify, but let's just leave it like that. So let's plug it in here now. So cosine of theta is U dot V, -22, over root 17, root 40. Okay? So I plug it into my calculator. Theta is inverse cosine. And like to reduce your keystrokes, you would do -22 over the square root of 17 times 40. Okay? So we have to just plug it into the calculator, inverse cosine, and that gives you 147.5. Okay? Okay, so let's see what it is that we've done, right? Let's just see, like, conceptually what it is that we've done. Let's draw vector U. It's 1, -4. That's vector U, yeah? Let's draw vector V. It's 2, 6. Okay? Does it make sense that the angle in between is 147.5? It does, right? That's what we found. Okay? Questions? No? Yes? No? Yeah. Uh-huh. What they are? So that's the magnitude of U, right? Each individual one. So this squared plus that squared. Okay? Okay, so now, okay, That's fine. I found the magnitude of U and V, okay? I'm sorry, I find the angle between U and V. But look, U and V was given to me in such nice, cute form. Yeah? Now look at how U and V is given right now. This is vector U, I and J, and then the other one is vector V, and you're just like, what the heck is that? Well, let's see. There is an angle 7 pi over 6, 7 pi over 6. Let's just see where exactly that is. Where is 7 pi over 6 these days?
In the third quadrant.
It is in the third quadrant, isn't it? So 7 pi over 6 would be just over, right? So right there. That's vector U, okay? Because, take a look. So what are this cosine and sine business then? Well, if I were to draw the components of this, look at this. The x component is the cosine of 7 pi over 6, and the y component is the sine of 7 pi over 6. Yeah. Isn't that cool? Say yes.
Yeah.
Yes. Okay. So that's what that is, all right? So that's vector u. Okay, so then where is vector v? It's at 5 pi over 4. Here. Okay? So what I need to find is the angle in between. So this takes you all the way back to geometry when you used the protractor postulate. Do you guys remember the protractor postulate?
No.
It basically says if you have one angle plus another angle, you can add them to find the total angle, right? So if from here to here, okay, so here it is. If from here to here it's 5 pi over 4, and then from here to here it's 7 pi over 4, how do I find the angle in between? I'm 7 pi over 6. How do I find the angle in between? What do I do? What do I do? Subtract them. That's all you have to do. So we're going to do 5 pi over 4 minus 7 pi over 6. And that's going to be the angle theta in between. So if you're walking down the street and somebody hands you this problem, you don't have to do all of this. You just say, oh, I just take one angle minus the other angle, okay? Like, okay, maybe you wouldn't be walking down the street. Maybe you're sitting at home doing your homework. That's what you would do, okay? Okay, so, and then you have to do like common denominator, blah, blah, blah. Doesn't that suck? But it's pi over 12, okay? All right?
Oh, wait, you don't have to express it like
In degrees? No, because, I mean, listen, it's pi day week. Radians are just as good. We don't discriminate. No. No. Okay? Yeah. Right? Like in dance, if they tell you to turn 90 degrees clockwise, you could just turn pi over 2 clockwise and you would get to the same place.
I don't think anybody's thinking.
Huh?
I don't think anybody's thinking. I'm turning pi over 2 clockwise.
Well, that's their problem, isn't it?
For the test, is it possible that we could have a unit circle because I'm gonna forget?
Because we're thinking, okay, where do I use this dot product? What is the importance of dot product? Okay, so take a look. Take a look. If I were to push this table, right, just across a little bit, right? I mean, one thing I can do, I say, okay, I need to push the table that way. I'll just like scoot down and just like horizontally push it. But that's annoying. Normally what I would do is I would exert a force like this in order to push it. And so the force that I exert is a diagonal force. But which way does the table move?
Forward.
Forward horizontally. Because my force is diagonal, but it's got a vertical component and a horizontal component. It's that horizontal component of the force that's sort of like contributing to the work I do in pushing this thing forward. So when you do work as defined in science, that's defined as the force you exert times the distance that something moves. But that force you exert has to be in the same direction as what the thing moves, right? So in here, so that's where the dot product comes in, right? So take a look. A person, oh, where's my diagram for this? My diagram went away. It's okay. So a person pushes a box with a constant force of 40 newtons at a constant angle of 45. So here's the box, and it's gonna move along the floor. Now, there is a force on this at an angle of 45 degrees. And that force is a vector. Find the work done in joules to move the box 12 meters. So the movement of the box, that's that vector B. It's horizontal, yes? So the work done is force times distance. But really, work is a scalar quantity, and it's force dot distance, F dot D. That means you have to take the magnitude of this vector B times the horizontal component of this, right? That's a dot product, okay? So work will be the magnitude of F times the magnitude of D cosine theta. So when you've got magnitudes and an angle, that's how you can do that. You can do that. So work will be 40 times 45, no, times 12.
Is it B or D? He's on there. He did B.
Oh, all right, I'll do D. Yeah. Okay, so times 12 times cosine 45. And when you put that in there, it'll be 339.4. I'll talk about units in a little bit, okay? I'll talk about units in a little bit. Okay, so this is how you find work. Okay, method 2. Remember how this is a dot product? Can we write these two in component form? What's vector D in component form? 12, 0. Good. Good. What's vector F in component form? Yep. Good. Yes. 40 sine 45. So now let's do F dot D. So let's do it using like the dot product. It'll be 12 times 40 cosine 45 plus 0 times 40 sine 45, which is how much? This goes away, but look, you still end with 12 times 40 times cosine 45, which is exactly what we ended up here, isn't it? You see how they're like exactly the same? Isn't that cool? It's still 40 times 12 times cosine 45. Okay, let's do a little bit of units. So force was in newtons. Distance is in meters, right? So the work is in Newton meter, which a Newton times a meter is a joule. You don't have to know that, just like extra information if you're ever like on Jeopardy and you need to know, or if you're ever in a physics class and you need to know, okay? But like this one, it tells you find the work done in joules, so you can just say like joules. It's a Newton meter. It's a unit of work or energy, because they're related, wouldn't you know? I know. Mm-hmm. That's power. Okay, no.